Hello everyone. Welcome to Shadetree Coding. Shadetree mechanic is an old-timey phrase with no standard definition. It's also a show from the 90s. To me, the phrase refers to an auto mechanic who works outside under the shade of a tree with the tools at hand, rather than in a shop with a lot of fancy equipment. I liked the phrase, so I adapted it for my own use. Once I had settled on the name, I wanted to create a tree logo to go with it, using the Python turtle module. I wanted an image that was both algorithmic and organic. The turtle module is based on a programming language called Logo. The original logo used an actual physical robot that looked a little bit like a turtle and had a pen attached which could be used to draw designs onto a sheet of paper on the floor. The logo most people who have used Logo have used draws lines and curves onto a screen, as seen in this BBC Nova documentary.
In a London school, 7-year-olds use similar instructions to drive an imaginary turtle on a journey round the planets. FD for forward, RT for right turn. By combining forward and turns, they can send it anywhere they like. Here, the turtle is an arrowhead.
It's often still called a turtle in reference to its origins, and that's also how the Python module got its name. After playing around for a little while, I was able to produce this simple tree line drawing. And then I started to imagine how cool it would look if it were animated. By default, the turtle module animates lines being drawn. You can make it draw faster or slower within some limits. You can also turn off this automatic drawing animation by calling tracer 0. Then you can issue multiple drawing commands and manually update the canvas once a complete frame is drawn. But by their nature, these two forms of animation are mutually exclusive. The first kind of animation is simple and requires no additional code. The second kind of animation requires some more code, but offers more flexibility. The solution I eventually came to uses both kinds of animation. My first unsuccessful attempt was to just do a screen capture of the tree being drawn, the first kind of animation. But I don't like how this looks. Even when I captured each section of the tree individually and then layered them together, it still didn't look quite right to me. My vision was that at each branch a new pen would be spawned, and then these pens would move simultaneously, looking a bit more like natural growth perhaps. But there's an issue. By the nature of how it's coded, the turtle module can only animate the movement of one pen at a time. I know this because I spent a good amount of time poking through the Python code for the turtle module, which you can easily find on GitHub. To make the animation I wanted, I would either have to recreate much of the turtle module's functionality, or I would have to do something a bit diabolical to the turtle module to get it to do what I want. I took the latter approach. I already had the beginnings of a plan. I could patch a particular method in the turtle screen class, which would allow me to record each point the turtle traveled to during the animation of a line or curve being drawn. To have a place to store this data, I also patched the raw turtle init method. When a turtle is created, it gets an additional attribute called animation. This starts out as an empty list, but fills up with, essentially, a list of points to travel along, so that I can replay the drawing animation with greater control. Instead of just putting points into the animation list, though, I actually used the partial function from the functools module to create drawing commands with the correct arguments pre-bound. To replay the animation, all I have to do is call the items in this list in sequence. But I still had to figure out how to allow different turtles to start at different times. My solution was to add some blank no-op frames to the turtle's animation list when the turtle is created. How many blank frames get initially added is determined by how many frames the current turtle has already recorded. Here's an example of what the process looks like. Notice that only one turtle moves at a time. First, turtle 1, then turtles 2, 3, and 4 in turn. After all the turtles are done drawing, one after the other, their motions are replayed like this. So, I mentioned earlier that I was going to patch some methods. What I mean by patch is that I'm going to temporarily replace some of the turtle module methods with ones of my own creation. In some cases, the replacement functions will call the original functions, but not in all cases. I ended up patching 5 methods, 4 in the raw turtle class and 1 in the turtle screen class. This is enough for me to create my simple line drawing. To capture more complete data like pen size and color would require just a little bit more work. My code starts out by caching all the methods that will be patched. Next, the replacement methods are defined. The init method is patched to add the animation action list. It needs to call the original init method. Methods that move the turtle around, like goTo and teleport, also call their original cached versions, because I want the turtles to go through all of these motions. The drawLine method is called from the goTo method. It updates the line on the canvas as the drawing animation plays out. I patch it in order to record these steps, but it does not need to call its original version. The remaining methods are responsible for updating the canvas. They don't need to call their original versions or do anything else. At this point, I want to suppress all of the drawing. I just want the turtles to go through the motions so I can record their steps. I've moved the logic and code for drawing the tree into a separate file called tree5. This function, branch 1, is defined there and leads to the whole tree being drawn. Once this process is finished, all the turtles are reset. At this point, I'm done with the patched methods, so all the originals are put back in place. Then, a loop goes through the pre-recorded steps and replays each turtle's animation 1 frame at a time. As a final note, it's worth explaining the zip and zip longest functions. With just a little bit of code, I can generate a sequence which contains the animation list of each turtle. Each animation list is essentially a sequence of frames for one turtle, something like this. But what I really want is a list of combined frames, where each item in the list is a list of every turtle's action for that point in the animation. The zip function is almost exactly what is required. It does what I need, except that its output is truncated to the length of the shortest subsequence. This makes sense because the behavior of the function depends on joining values across lists by index. So once one list runs out, it's not obvious how it would continue. The zip longest function, however, is exactly what's needed. And to make it work, you have to give it a value to pad out shorter sequences with. And here I've used none, which is my no-op command. And that's it. I hope you enjoyed this video, and I hope you join me next time with more Shadetree Coding.